So now we continue our ALF Basics, which explains some details of the implementation in ALF. And today we have Francesco, who is a long-time contributor to ALF and with us here in Würzburg. And he's going to be talking about how observables are written in ALF. Francesco? We don't hear you. Okay.
Thank you. Thank you for the introduction. As Jefferson mentioned, this is the topic of this lecture will be an introduction to the observables as they are treated in the ALF package. Here is a brief outline of the lecture. I will start by introducing some of the basic features of the internal storage used for the type of observables that we have in ALF, the type of that we have and how they are stored. And then I will move on to present at least some of the predefined observables that are already inside the ALF package. I will not cover all of them because there is a very long list, but I'll give you some reference to that. And finally, I would like to close by giving you some hint on how you can define and program your own observables if you need some new observables that are not yet present in the ALF package. So before I go on, so let's get started by the first topic. Before I go on, let me give a very general remarks. In general, for a given quantum Monte Carlo configuration C, the action may not be positive real, and this is leads to the infamous sign problem, which often is a major obstacle to simulate numerical models, but as long as the sign problem is small, one can live with that. And the way to tackle this is to perform essentially a reweighting. So one can show that one can only simulate a positive definite measure. So to tackle a non-positive definite measure, one has to do a reweighting. And as you can see in this formula, the expectation value of generic observables is obtained as a ratio, where on the numerator I have the average value of an observable times the sign and the possible phase factor. And on the denominator, I have the average value of the sign. And as long as this is not too small, one can still get reasonable results. You can see from this expression that in general, you need to compute an observable, you need not only the value of the observable at the given configuration, but also you have to multiply this value by the sign and the phase factor, and also you need the sign factor in the denominator here. And the ALF package already takes care of this. It always multiplies all the observables by the corresponding factor, S times ZP for the observable, and also takes care of the sign, or the cumulative sign, in order to perform this reweighting. So let's move to the first type of observables that are present in ALF. The most basic type of observable are the scalar observables, so just numbers. Think about, for example, the magnetization or the energy. At this point, I would like to recall that at the given configuration of the quantum Monte Carlo, the translational invariance along the imaginary time is broken. It is only restored after a Monte Carlo averaging. This also suggests that in order to get an improved value of some scalar observable, you may measure this scalar observable at different time slices and then average the results in order to get a more stable, more precise result. This is controlled by some specific parameter that you find in the name list var_qmc inside the general parameter file of the ALF. Specifically, these two LOPS start and LOPS n, which gives you the starting and the end slices in the imaginary time where the scalar observable are measured and averaged. How they are stored, the scalar observable. So in general, we have a specific derived Fortran type, which we call observec, that allows to store the scalar observable, and for giving better generality, we also allow for a vector of possible scalar observable grouped together. These are the public fields of this Fortran type observec. You see that we have n, which is a cumulated integer that takes time, which is takes care of the number of measurements that are done. So it is increased by 1 whenever you do a measure. and as well as the average sign, which is the one that enters in the denominator of the reweighting formulas. Obsvec takes care of is a vector of the cumulated scalar observables, which are already multiplied by this phase and sign factor that you need in order to do a possible reweighting. There are some other fields. There is a file vec, which is just a string and takes care to give the name of the file where these observables, the final Monte Carlo beans, will be saved to. Now, the library always, for scalar observables, always add a suffix underscore scal. So whenever any file you insert here, the output will be saved into this file vec underscore scale. There is also two other fields. One in analysis mode is a char field, a string that gives you a hint on how the vector should be analyzed. The typical simplest case is the identity, means that you just have to compute the expectation value, like for example in the energy. But for some more complicated observable, you may need to compute some explicit function of the Monte Carlo beans, and this analysis mode is the field that gives you this hint. Description is also another optional character field, which gives a description of the scalar observables. Beside the output file vec scal, where the beans are saved, there is also the library also generates and saves the file vec scal info, so appending the suffix scal and info, which contains this information about the scalar observables. Another class, large class of observables are the equal time correlation functions. These are the observables that you need whenever you need a spatially resolved correlation of some values, like the Prince function or the spins or the density correlation, as well as when you need some Fourier transform of them to study what is the dominant vector, momentum vector, for example. These are generically observables which are written in this way, where I given an observable O at a local observable O characterized by a lattice site I and possibly some other indexes alpha, which could be, for example, the orbital index inside a unit cell or some other additional flavor index. Equal time correlation function are expressed as the connected part of a two-point function between a site I and a site J. These are, for example, some example of this computation for a charge-charge correlation or a spin-spin correlation on a paper of a few years ago. As you can see from this formula, I have already written the Fourier transform for the reason that the ALF library already takes care of computing the Fourier transform. Next to the equal time correlation function, there are also the time displaced correlation function, which are conceptually very similar in that now we have, however, an additional parameter, the time tau. So we compute the displacement in space and in time. And as before, we do automatically, we have an automatic computation of the Fourier transform. Now for the time displaced correlation function, it's useful to observe that they can be expensive in terms of computational time. So you may not necessarily always want to compute this time displaced correlation function. And the activation of this routine is controlled by another parameter in the var QMC name list. This parameter is called L tau. When it is set to 1, you compute the time displaced correlations. So how are these equal time and time displaced correlation functions stored inside the ALF? So there is a Fortran type, which is called obserlat, whose public member fields are this one here. We have, as before, a field N that contains the number of measurements, the average signs that you need for the reweighting. We have now an obslat member that contains the cumulated correlation function. So now it will also depend on the index I minus j on the Bravais lattice, and possibly on the time tau if it is a time displaced correlation function, and on the orbital indexes or the additional indexes alpha and beta that comes in the formula of the product. If you look at the formulas of the two-point function, we are generally interested in the connected part of the two-point function. That means that we subtract the square of the expectation value of the operator. And for that, we need also to keep track of the accumulated expectation value of a single operator, which is now stored in this other obslat 0 member of obserlat. Then we have, as before, a file lat char, a string which contains the name of the file where this specific correlation will be saved to. And the library automatically append a suffix underscore ec for the equal time correlation, or underscore tau for the time displaced correlations of the file name that you give where the beans will be saved. And as before, we have also an info file, which in this case for the equal time correlation function will be the same file lat with underscore eq info added at the end, and underscore tau info for the time displaced correlation function. Additional member fields that are needed to store the correlation function are a pointer to the underlying lattice, Bravais lattice structure, the point to underline the unit cell. These are needed, of course, because to treat the observer, we need to know what exactly is the geometrical structure of the lattice and the unit cell. There are two other fields which are the imaginary time delta tau, and the channel which I will cover here, and it's used to do the computation of the spectral function using maximum entropy methods. So these are the basic Fortran type where our data are stored. You don't need to implement many of the observables which are commonly used, because the ALF already provides some sets of predefined observables. There is actually an ever-growing list of predefined observables. I won't have the time to cover all of them, but I'll try to give you what are the main principles. We decide by convention that all the predefined observables are obtained by calling to a subroutine called predefined underscore ops underscore some other name, depending on the observables. And this subroutine generically takes a list of parameters. Now, not every observable takes all the list of these parameters, but some of them are common to all the predefined ops subroutine. In particular, all these routines need to know what is the lattice and the unit cell, so you pass them as a parameter. They need generically a list of sites, which for many of these predefined ops is a two-dimensional array, which is usually it's already constructed inside the program, that gives you a correspondence. Given a physical lattice site I, you provide in the first element of list I the corresponding Bravais lattice position, so the position in the Bravais lattice, and the second is the corresponding orbital index inside the unit cell of the model. We have other parameters which are not always needed depending on observable, are the imaginary time slice NT. The Green's functions, which are always due to in the very nature of the auxiliary field simulation, the Green's functions are always available, and they are of course needed to compute every observable through the use of the Wick's theorem. So depending on the type of observer, we may need the equal time Green's function to input, or the time displaced Green's function. We also need, depending on observer, the number of colors and these two phase factors that I have already talked before. Obs is generically one or more measurements of the output of the subroutine. So let me give you a couple of examples to see how this is implemented. So the first one is a spin-spin correlation for SUN invariant model. That means for models which are SUN invariant and for which you have chosen a Hubbard autonomous decomposition that preserves this SUN invariance. Then it means that at every Monte Carlo configuration, we have a full SUN invariance, and this routine essentially gives you the spin-spin correlation summed over all the component of the SUN group. Now, to have a concrete example, think about a Hubbard model, a standard Hubbard model with enjoys an SU2 symmetry. You introduce a Hubbard autonomous decomposition that respects the symmetry, and then this is the implementation inside the alpha is then obtained by having a single flavor for fermions and the value of NSUN equal to 2, so S2 symmetry, and this observable just gives you the spin-spin correlations. There is also a generalization for more than one flavor number, and you can refer to the documentation to see exactly what is computed. A closely related subroutine is the spin MZ measure subroutine, which takes care of doing practically the same thing, the spin-spin correlation, but having in mind a Hubbard-Satonovich decomposition or a model that breaks explicitly the full SU2 or symmetry. For example, it could be a Hubbard model, which is SU2 symmetric, but you use a Hubbard-Satonovich decomposition that couples to the magnetization. Thereby, you have two flavors and n is 1 equal to 1. And in this case, you have then to distinguish between the ZZ component of the spin correlation and the XX and YY, which are provided as output ops Z, ops XY of this subroutine. And then also this subroutine, for convenience, also gives you already the sum, so the total average. We have also the time displaced correlation with a similar syntax, except that now they acquire as a parameter the time displaced Green's function, the SUN invariant case, as also the spin Z MZ case. And there are many others. There's Green's function, dimer correlations, charge correlations, Kondo or co-tunneling functions. There is a list which is growing practically on every release. Now, one new release, one new features that is on the ALF version 2 is the computation of the entanglement entropies. So very shortly, what are the entanglement entropies? What are we interested? So there is a growing interest of using entanglement to study condensed matter problem. The simplest case is to use the bipartite entanglement, where you divide your Hilbert space into two places, A and B. You trace out the degrees of freedom of B, and you get a reduced density metric of A. And from this reduced density matrix, the moments of this row gives you the so-called Renyi entropies. Now, when you do a real space partition, the entropies generically, in many cases, obey an area law, means that they are proportional just to the area between A and B. And corrections to the area law are associated with a lot of useful information. For example, they are associated to the central charging, conformal field theories in 1+1 dimension. For symmetry broken phase, they are related to the number of Gaussian modes, and so on. There are many applications, and you can refer to this recent review for this application in condensed matter. Now, the ALF2 allows you to compute the second Renyi entropy. This is provided in a new module called entanglement model.f90. It only works if you have an MPI environment with at least two tasks for the way they are computed. And the second Renyi entropy is obtained by calling this subroutine predefined ops scal Renyi ent. You see that what are the input parameter? Beside the GRC, which is just the Green's function equal time that you need to compute this every equal time observables. This routine needs 2 or 3 parameters, list and site and SUN. So we have provided 3 different specialization of this routine. The most general case is that when the subsystem A, for which you want to compute the Renyi entropy, is specified by a 3-dimensional array, which for every flavor and SUN color gives you the list of lattice sites. And then next to this, you have to know what are for every flavor and SUN sites, how many lattice sites there are. In this case, then you don't need anymore this NSUN parameter. A specialization for the case where the color index is shared by all flavors is obtained by having then a list, which is a 2-dimensional array that for every flavor gives you the list of lattice sites. Now, n sites is just a 1-dimensional array giving you the sites, the number of sites for any flavor index, and then you need the number of color for every flavor index, which is then provided by this NSUN parameter here. And finally, the simplest case where you have a bipartition and a subsystem A whose degrees of freedom share all the same flavor and color indexes is this one here. And in this case, list is just a 1-dimensional array with the number of lattice sites, the list of lattice sites, and n sites and n sun, they contain the number of sites and the number of color indexes. Okay, so another routine that you find that I would just mention, you can find more information in the documentation, is the so-called mutual information, which is a combination of the second Renyi entropies when one considers 2 subsystems A and B, and one wants to study the entanglement between these 2 subsystems. And the mutual information is defined in this way as the combination that takes care of the secondary entropy for the subsystem A, B, and then you subtract the union of A and B. This is called by calling this subroutine obscal mutual information, and the syntax is the same. The only restriction that we allowed the same NSUN for to be the same between A and B. Okay, so maybe in the last minutes, I can tell you a bit about how you define your own observable. So what do you have to modify the program in order to implement your own observable? So the observables are defined inside the specific Hamiltonian submodules. For example, if you look inside prog Hamiltonians, you will find the Hamiltonian Hubbard plane vanilla S mod, which is the submodus for a simplified Hubbard model. Inside these submodules, you will find these are the three routines that you have to look for and eventually modify. There is a subroutine alloc ops, which takes care of defining all the kind of correlation observable you want and allocates essentially the memory. There is an observable, a subroutine observe, which is where the equal time correlations or the scalar observable are computed. So if you want a new observable, you have to insert here the new observable in alloc ops, and then also here in observe. If you're interested in having a new time displaced correlation, then they are computed in the subroutine observe T. You see that the syntax already tells you that in this case you need the Green's function. In the observe T, you need the time displaced Green's functions. How you define a new observables? You have to take in mind that the Wick's theorem holds for every Monte Carlo configuration. This means that any kind of observables which are written in many body forms in terms of creation and annihilation operators can be written in terms, applying the Wick's theorem in terms of the Green's function of the model. For example, if I have here a two-body terms which contains two creation and annihilation operator, applying the Wick's theorem, I can reduce this expectation value on a given configuration as a product, the sum of these two products. So the contraction, the first with the second, third with the fourth, and then the other contraction coming from the Wick's theorem. And you see on the right-hand side, what you have is nothing but a combination of the Green's function of the model. Now, it is built in the auxiliary field simulation that these Green's functions are always available, and actually they are also the argument for which you call observe or observe T. So the Green's function at equal time or the time displaced Green's function. So with that, inside the routine, if you want to add a new observable, you already have this Green's function, and performing or computing by hand or with a mathematical notebook the actual contraction, you can define your own observables. One thing to notice here is that if you're interested in time displaced observable, because of the way that the program is done, when you're updating a specific time slice tau, you have access to the Green's function that contains the time displaced Green's function that contains the index tau and or the index 0. So you can only insert the index tau 0. This is why the observe T contains only these four time displaced Green's functions, which are this four combination here. Now, I'm almost at the end of the presentation. ALF is a collaborative environment, a joint project of many peoples. If you think that something is missing, that some observables are of particular interest or they are needed for a specific project, please go to our GitLab server and open an issue. Or even better, you can also work yourself out a solution for the observable, and you can share it on our GitLab, and we are happy to receive a contribution from interested users. With that, I think I'm finished with the presentation, and I'm happy to take questions.
Thank you, Francesco. Very nice. So perhaps you can stop the recording, and I have time for questions.